Welcome back, everybody. It was very nice to chat last time about how to generate conjectures using machine learning in pure mathematics. And today is going to be a slightly different kind of a session. So it's going to be very hands-on and a lot more interactive. So feel free to stop me and ask questions or make comments or suggestions. So the plan of today's talk is to first take you through a very simple example for machine learning in a practical setting, and we'll follow this up with a little bit of recap from the last time, which will help us put into context the next case study that we will conduct. So the first case study that we will begin with is about handwriting recognition, and we will be using Mathematica for that. And the second case study will be about finite simple groups. So if you've got your Mathematica notebooks with you, then we'll start with that. Right. The first case study we'll do is handwriting recognition. So I'll open up my Mathematica notebook at this end, and let me know if you cannot see it. Can you see a notebook?
Can you hear us?
Yes.
Okay.
We have issues at the moment here with EduRoam. We don't seem to be able to connect to EduRoam.
All right. Take your time.
Yeah, sorry, Challenger. We are still technically challenged here.
No worries. EduRoam has got a mind of its own.
Not just EduRoam. The
Gabriel. They're having connectivity issues over the whole building. I see. Okay. Yeah.
So, okay. Okay, we proceed now to share the notebook with Gabriel here. Okay.
All right.
Okay.
All right. I can share this notebook perhaps. Again, for the next following case study, we'll need a text file that I had made available. So you might have access to it. Otherwise, I'll again send it to you after the lecture. So to begin with, this is sort of an interesting choice of example for this audience, mainly because this has to do nothing with mathematics, but to do with something that is widely used as a test bed for machine learning. And it's a very informative exercise to be able to write down some basic machine learning codes to recognize handwriting or handwritten digits. So the data set at play is called the MNIST data set. So let's first try and acquire it. If anyone indeed has a connection, then they might be able to get this resource. So it just collected all the data from the MNIST dataset, and I'll show you in a moment what this data actually looks like and what's the inference task that we have at hand.
What is the MNIST database? What is the MNIST?
Yes, so the MNIST database is a collection of handwritten digits, and there are gazillions of examples of that. So imagine you are writing down the digits in your own handwriting from 0 to 9, and you have also labeled them. So I'll show you in a moment when it's able to load. Let me quit the kernel and restart. I wasn't anticipating this error, but that's interesting. Let me just check. Okay, should work now. All right. I've made an error. Right. So so this contains 60,000 data points, and you might ask, as I was just asked, what the data might look like. So let's create a small sample of 1,000 data points, and let's randomly sample from this data. Let's randomly sample 1,000 data points from the set of 60,000 data, and let's have a look what this actually looks like. Right. So this is the data that we are planning to work with. So if you look at, so I've just displayed 20 random data points from this data set called MNIST, this data set of handwritten digits. And as you can see, they are, this is a data set of handwritten digits. So the first example is in someone's handwriting and represents the digit 9. So it's labeled as 9. The second example, the second data point is the number 5 that is written in that's written in someone's handwriting, and it's labeled as 5, and so on and so forth. So this is the sample that we will that sort of demonstrates what the data set looks like. Now, in a machine learning pipeline, and again to emphasize that this is a rather basic application of machine learning to recognizing handwritten digits, and as such will employ very simple machine learning architectures. In our case, we'll use a neural network. Now, if you have any questions at any point, please feel free to ask.
So here
Yes.
you've loaded a database of handwriting samples.
Yes.
And this handwriting samples is meaning that it's a collection of random. I mean, it's a collection of and it's already pre-labeled.
Yes.
Basically,
Yes.
the handwriting has got like this.
I don't hear very well. Could you repeat that?
Sorry,
So I
sorry.
hear parts of the sentence, but then yeah.
Can you hear me now?
Yes.
Yeah, everything is breaking apart here. Sorry. Even so this is a training set. We've got like handwritten numbers. So
Yes.
1, the 5, the 106. And it's already associated. The label is associated to it. So if it's a 1, 5, it's not associated. Right?
Okay, from what I gathered, yes, it's labeled. It's kind of breaking up, so I'm not sure. Maybe try talking slowly. I see you waving your hand, but I don't hear anything. Yes, yes, I realized. Yes. All right, all right, all right. Thanks. One possibility could be if anyone's on Zoom and would like to type in questions, that will definitely reach me. So I'll just carry on for the time being. All right. So in the interest of answering as many questions as possible, I'll try to be very detailed. So effectively, we have this data set of 60,000 handwritten digits. Of course, there are only 10 digits that we are working with here, and the handwritten digits have been labeled. So for example, as you can see on the screen, In the first one, you see the handwritten digit 9 is labeled as 9, so everything is labeled correctly. And the labeling is denoted by the arrow here. Right. And yes.
Okay, quick question. Does it matter that the sample doesn't have a 2 in it?
Doesn't have a 2 in it. Oh, yes, of course. I mean, I assure you it has 2 in it. So let's randomly sample again, and perhaps we'll have a 2 here. So yeah, so here there's a 2. Yeah. All right. So so the idea is that we have this huge data set. So how do we get a neural network to learn to recognize these handwritten digits? So we'll think of the learning exercise as an input-output map, where the input are the pixels on the image that contains the handwritten digit, and the output is the label. So in the data set, this is already listed out, and we are trying to come up with a neural network which will automatically be able to do this with some reasonable degree of accuracy. Now, in standard machine learning practice, one ought to avoid biases. So typically, you would work with a training data, and you will set out the remaining data on which you can test out the learning outcomes. So effectively, what will happen is, from this data set, which contains 60,000 of these examples, we will only choose a random collection of 1,000 of them, and we will use that data to learn or to create this input-output map through a neural network. And following this, we are going to test the learned neural network on this unseen data, which is often called the test set. Now, there are various interesting things to say here, and I'll touch upon one or two of those. So, so typically, when you so effectively, to begin with, you're partitioning your data. So you have, in our case, you have a data set of 60,000, and as I was saying, we'll use only 1,000 of them to train the neural network. And once it is trained, we will test it on the remaining data. But a real pipeline might be even more nuanced than this. You might be breaking the full data set into 3 parts: training, that you will actually use to get the neural network to learn. You will set out another part which is called a validation set, and the third part will be the test set. So test set is untouched in the training process to avoid any biases, and the role of the validation set is to help you determine what is the things like the simplest architecture that might be able to act as a predictive model on the unseen data, which is in the test set.
Daniel, question.
Yes.
So now the internet's back. We're trying to run the code again. So every time I run data, it says $.
It says.
Oh. No, okay, sorry. Now I see. Okay, thank you. Sorry.
All right, great. Does anyone have any issues executing this part of the code so far?
Fine.
All right, great. Right. So as I was saying, the machine learning pipeline can be complex, but the basic things I'm mentioning here have to do with partitioning your data into different parts that might help you learn from a limited amount of data, and then you can test the outcome on unseen data. And that's sort of the proof of the pudding that we might need to establish that, okay, our machine learning process has indeed worked, and we can actually recognize handwritten digits to a reasonable degree of accuracy. Accuracies are sort of are a measure of your performance. Yes. All right. Accuracies are a measure of your performance, and there are various notions of metrics with which you can evaluate your machine learning outcomes. So to proceed, let's define. Yes. Is there a question?
No.
All right. Okay. So let's define a neural network. Now, one of the reasons I'm doing this on Mathematica as opposed to something more commonly used in machine learning, which which might be things like PyTorch or other basic things like Keras, or more interesting things like TensorFlow, etc., is that machine learning entered the mathematical physics community at a time when it sort of the timing coincided with the introduction of machine learning modules in Mathematica. And one of the earliest papers written on this front was by Yang Hui He, who you might have heard about or heard from rather in this workshop. And so in that, Yang introduced machine learning to the mathematical physics community by alluring them with Mathematica. And the application that Yang had made had to do with building neural architectures that can accurately predict Hodge numbers of certain Calabi-Yau geometries, namely complete intersection Calabi-Yaus. And there was an existing data set computed in the late 80s through efforts by lots of people, ultimately resulting in this data set of complete intersection Calabi-Yau manifolds that Philip Candelas put together. I'm given to understand that it's one of the early examples of a data set in algebraic geometry, and presumably computers at CERN were employed to complete that task. So with that background and motivation to using Mathematica, let's write down our first neural network here. Before that, let me mention that there isn't a neural network that sort of is the solution to the prediction problem here. Rather, an entire class of neural networks will be able to accomplish the task with equal ease. So, and there are various ingredients at play here, and deep learning, which is effectively machine learning using neural networks, which are wider than 3 or more layers, are the architectures that we'll be employing here. And there are a myriad of interesting phenomena that occur in the context of neural networks and how they accomplish learning tasks themselves. And this is an area of active research, and there are various open questions. The manner in which you might determine the most generalizable architecture in this is sort of a source of very interesting questions. What does generalizability mean here? So in this context, generalizability means that it's your ability to use this kind of architectures to predict on unseen data or out of distribution points. And that is a very tough problem, and there's lots and lots of interesting experiments and theoretical explanations of them that drives the field. So in some sense, the field of machine learning at the moment is a bit like the state of particle physics in the 60s, where experiments and theory were driving each other. So there's a lot of research in machine learning that is motivated purely by conducting experiments on different data sets and combining and coming up with new methodologies for training and testing and developing the field as such. So without further ado, let me write down a neural network. Now, this is rather simple to write down in Mathematica. So here is this first interesting module called the net chain. So I'll open the help here. So, okay, so, I should also mention that one of the reasons it's very useful for mathematicians and physicists who are not big fans of writing down tons of lines of code is documentation. So Mathematica is extremely well documented, and this is an advantage that Mathematica has. There are limitations, so you have you sort of have much less of a handle in your machine learning modules when you are working with Mathematica. So at some point, when your machine learning task gets more and more complicated or more complex, rather, then you might consider using other kinds of modules or frameworks such as PyTorch, TensorFlow, etc. Right. So NetChain basically creates a neural network which you can design by yourself. And there are diagrammatic ways of doing this, but in essence, as perhaps we all know, a neural network is effectively a function class. It has a bunch of parameters called weights and biases, and it accepts some inputs and it gives you some outputs. And the architecture is sort of modular, so you can plug it into different parts of your machine learning pipeline, and effectively you use it how you fancy, depending on the problem at hand. In this example, we will do something rather basic. So we will specify what are the layers of a neural network and the activation functions. So perhaps everyone is aware what these terminologies mean, but the function class that a neural network represents can be written down as a composition of functions. This composition in the context of a neural network is effectively a linear transformation of a vector followed by the addition of another vector, and you pass the resulting vector that you obtain through some nonlinearity. And this nonlinearity is called the activation function. So defining a neural network is therefore equivalent to writing down what these layers are and writing down the activations in between, interspersed between them. So, right. So there's going to be lots of interesting kinds of functions that I'll write down here, and I wouldn't want you to get too bothered with these definitions because they fulfill specific functionalities. So the first layer that I'm writing down here is a convolutional layer, and a convolutional layer effectively gives your neural network translation symmetry with respect to its inputs. And this is sort of very interesting, historically speaking. So imagine, if you look at any of the images here, they have been labeled nicely. Now imagine the the handwritten digit, the picture of it is not in the middle. It's sort of, you know, in some other position, and we should be immune to that, right? Our outputs should be independent of this translation. So therefore, to incorporate such translation invariance, we use something called a convolutional layer. And effectively, as I was saying, it gives you translation symmetry in your network. Now, in the 90s, when the convolutional neural networks came about, they had a big impact in the field of computer vision. And it was sort of, as far as I know, the first instance of an architecture which was incorporating a symmetry that's also realized in a physical system. So as we all know, that Newton's second law, you know, in the absence of an external force, momentum is conserved, is practically equivalent to translation symmetry in nature. And of course, it took 20 years to build build in other kinds of neural architectures that are symmetric with respect to other symmetries. But that's certainly not due to lack of technology available during that time, but rather the use cases were not fully determined at that time, and the ability to train large networks wasn't quite there as much. So so the first layer is a convolutional layer. Following this, we will add an activation function. Let me write. So the activation function I'm going to use here is ramp. So ramp, just to demonstrate what ramp is as a function, it's basically the following. Ramp of x is basically x if x is positive, and otherwise it is 0. So following this transformation, every element of the vector you produce after this first composition is either positive or 0, which is very useful as a tool, because we're going to add more layers. And if we add a ramp layer, or a, the popular name is ReLU, rectified linear unit, this ReLU activation guarantees the positiveness of your output, positivity of your output if you add it at the end. Now, in our context, it is kind of useful because our outputs need to be between 0 to 9. And as such, it's useful in this context. There are various ways of setting up this problem, and we will be going about things in the following way. Next, we're going to add another layer. It's typical to use this layer after a convolution layer. It helps you aggregate the outputs. We're going to add another convolution layer. These are the parameters within. They denote dimensions and your averaging parameter that guarantees translation invariance. Next, we'll again add another activation. So again, we choose to add ramp. Typically, you can use the same activation, and there are other examples of activation functions that you might choose to use. So, for example, one can use tan hyperbolic x, which looks like this, and so on and so forth. You can use something like logistic sigmoid, which let's increase the range so we can see its behavior. Yeah. So the green one is a logistic sigmoid activation function. The yellow one is the tan hyperbolic activation function, and the blue one is the original ReLU or ramp function. So we include these architectures. Let's include another pooling layer. And let's flatten out the outputs. Let's add another linear layer here with 500 nodes. So one of the nice things about using Mathematica is how easy it is to use. So 500 means you add a layer which has 500 nodes in it. And effectively it denotes matrix multiplication of the previous, or the vector coming in from before with a very large matrix related to the size 500, and you pass it through. Now following this, this is a linear layer. So I could have alternately written linear layer 500. Then we add another activation. Then we add a smaller or smaller number of slightly shorter linear layer, which has only 10 nodes. So now my network architecture is sort of tapering off. And followed by, let's add a softmax layer. So the softmax function, as we know, effectively does the following transformation. It takes an input. It's actually, well, I mean, we have we can this. Yes. So if you have a look at this highlighted part of the screen, the softmax layer n, when you apply it to some input array, it produces another array, and it basically does this transformation where it exponentiates your vector, and it sort of normalizes it by the sum of exponentials of all your vectors. And in effect, what this means is you can convert your outputs into probabilities. And that's sort of useful. So you could say that, okay, I'm going to design an architecture where my input are all these pixels coming from this data, and the output is let's say you have 10 output channels. So the output is a vector of size 10. But when you pass on an image, let's say 4, the output you might get would be some non-zero numbers on these various output channels, of which there are 10 because they denote the digits 0 to 9. So if you apply a softmax transformation in the penultimate layer, it's effectively converting whatever vector had appeared before it into a set of probabilities. And what might end up happening when you input the image corresponding to the handwritten digit 4, the channel, the output channel corresponding to 4, so it will go as 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. The output channel corresponding to 4 might have the largest probability, and you choose to pick that up. So therefore, that would be your prediction from the neural network. All right. So we have defined our neural network, and now let's see what this looks like. So we execute this. Now let's look up some information. So this is sort of the architecture that we have written down here. If this is boring and everyone knows about this, please stop me, and then I'll move faster.
No. Please go slower. I mean, yeah.
All right, Suresh. Okay. So, assuming everyone is with me so far. So, yes. All right. So here we have an input layer which accepts the pixels of the image as input, and it passes through a convolutional layer which makes your network architecture translation invariant. then you add a pooling layer, which sort of aggregates the outputs from the previous layer. It passes it on to another convolutional layer, passes through activations, and it keeps going on and on until the output layer, which is a vector of size 10.
Can you say what this, just the building block, this convolution layer 25, what this does? Just this convolutional layer?
Yes, so it sort of think of the Reynolds operator in invariant theory. You sort of are averaging over some group action to make the quantity invariant under a certain symmetry. So in this case, it is the translation symmetry that we are talking about, and the convolution layer implements exactly that.
Okay. But the dimensions then 20 and 5?
Yes.
What? Okay.
Yes. So so it depends on the the number of output channels you might want to have, and the size of the kernel it uses to compute the convolution. So when you convolve, you can think of it as some sort of an integral that's sort of computed by passing some smaller box of some size s cross s across your different parts of the input, and it helps you build in the translation symmetry.
Anders, quick question again. So now I should think of these. So why are convolution layer and linear layer in red here?
Oh, that's sort of well, short answer is I don't know. But if I had to guess, I would say that it's sort of in red because you're sort of you have not initialized this network. And the act of initializing this network would be to assign random values to the parameters that that help you specify or instantiate your neural network.
So can
So,
I what the role of ramp? You said it's an activation function.
yes.
Does it mean that if so that you have like a function that's your input, like whatever, like some vector or x or whatever it is, and it passes through a convolution layer. So this is the first function in my neural network. Then okay, that's just some convolution function, and then whatever that convolution function outputs, it gets sent to ramp function. Now, if the ramp function basically gets activated, meaning that if the function, when it gets input into the ramp, satisfies the condition that, whatever, like let's say ramp gives you an output 1 or 0 or some non-zero answer, then it passes to the next layer, the pooling layer.
Yes.
So for example, if you use the ramp as in what you did, the standard ramp function, which is x if x greater than 0 or 0 if x less than 0, meaning that if the convolution layer of the input is going to be less than 0, the ramp won't activate for that particular data point.
Well, it will give you 0.
It'll give you 0, exactly. Yeah, I see. Okay. And then you go to pooling layer. This is where I'm lost. What does the pooling layer do again?
Yeah, so pooling layer is basically something that's is I don't want to say customary, but it you can use it after a convolution layer, and it sort of reduces the well, it sort of aggregates your outputs coming from the convolution layer, so basically it reduces the dimensions of your vector that's constantly being propagated.
I see. So,
does that make sense?
sorry, no. There's some other guy telling me here what to do, or giving another. Okay. Well, that's what pooling layer does. So, okay. Sure. Okay, I see. Okay, and is it always customary to go convolution ramp pulling, or is it
Uh-huh.
you
So
switch the architecture a bit?
yes, absolutely. And this is so important. There is nothing set in stone in terms of your architecture design. And architecture design should be informed by your problem at hand. I know this kind of an architecture will potentially give you good results. So that's why I'm choosing to work with this. But this is not to say that some other, completely different architecture won't.
Okay, let's see.
Yeah. So this is, yeah, go on.
I've written down, let's say, for example, I've written down this net shape.
Yes.
Is there a way or like some sort of a measure to say that whatever we've written down is the net shape is the neural network?
Sorry, is there a mechanism to say?
Is there a consistent way to say, for example, like let's say, for example, if this were matrix multiplication, you can look at the dimension of the different matrices, and then you would say, okay, because basically like if you want, you just need to know that the number of rows and the number of columns have to be, like in correspondence to each other. Only then can you multiply the matrices. Is there something similar here I can say to see if whether whatever you define in there actually makes sense?
Yes, absolutely. You're precisely correct. So that's exactly what's going on here. And those numbers are determining the arguments in these functions. So, 25, 2, 2, etc. And the reason is, imagine your input was X, and when you pass it to through the neural network, what's happening is you are multiplying. Imagine X is a vector. You're multiplying it with a matrix W1. You're adding another vector to it. This W1 is called a weight matrix. B1 is a bias vector. And then you are passing it through some nonlinearity, which I can denote by sigma, or let's say this is your ramp function. And then you sort of multiply this with another weight vector, a weight matrix, add a bias vector to it, and then you pass the whole thing, the activation again, and you keep repeating. And so on. So you are precisely right that this is indeed it is just matrix multiplication followed by nonlinearities.
Okay, thank you. One question.
So just to make sure, when you're taking two convolutional layers, you're getting like the second one is basically this 50 kind of read, and then you reduce.
Sorry, you're cutting off. You're saying when you take a second convolutional layer, what's the question?
So basically at step 8.
Mhm.
So everything that you get out of the convolutional layers are put in terms of a linear layer with 500 units, right?
Sorry, the connection is a bit. Sorry, let's try one more time.
Okay.
Yes, go ahead. Sorry, I'm not catching this.
Okay, no worry.
Oh, no, I heard that.
Okay, so at step 8, you have a linear layer.
Yes.
This linear layer is a layer with 500 neurons, right?
Yes.
Okay, and then basically everything that you're reducing to your convolutional layers in steps 1 and 4, now you're turning into a linear layer of 500 neurons, and out of these, you get a 10-dimensional output.
Yes.
Okay.
No, out of the linear layer, I'm getting a 500 dimensional output. So it's outputting a vector of 500. Yes.
So at step 8, but step 11, you just get a 10-dimensional vector out of it.
Yes, because I have added another linear layer which reduces the dimensions.
Exactly. Okay. Okay. That was
Right. All right. Okay, great. So there is something called net initialize that one can consider doing. So for example, we can net initialize this first layer is not fully specified. Okay, well, you can initialize this. Let's park this for the moment. I don't want to get too much into debugging. All right. Are there any questions at the moment? All right. If not, I'll proceed. All right. So we have acquired our data. We have declared what the architecture is. The parameters in these weight matrices and bias vectors are unspecified. So now our goal is to determine those parameters such that the network is not only is able to learn from the examples and become predictive on unseen data. So in some sort of a sense, this is a bit like saying learning is compression. So you are, you're trying to write down a function that takes as input some handwritten digit and the pixels of the image of a handwritten digit and gives you an exact number. So this is, this is the task that needs to be accomplished with training. So let's try to train this network using this function called netTrain. Now, this requires two quantities. One is your architecture, which is lenet, and your data, which, if you remember, we had gathered through sample. Just a quick reminder what this sample looks like. It looks like this, right? And how many data points do we have? We have 1,000 data points. All right. So now, of course, this is a very simplified version of what is how you might actually use a neural network in your problem of interest. And and there are various ways of training. There are various handles to this training procedure. So why don't we first let Mathematica choose what these Mathematica automatically can choose these various parameters, and we can discuss some of these things after it has trained. So right now it's sort of learning through gradient descent. So in effect, it's trying to solve an optimization problem in a very large number of dimensions. So, if you think about all the unspecified parameters in all the weight and bias matrices that appear in your architecture, it is immense. I think in this case, it might be of the order of tens of thousands. Now, how do you formulate this optimization problem that it is currently solving? You sort of say that, okay, you have not specified the neural network function, but you make a forward pass of an input. It gives you some output. Now, the output, think of the output as depending on these, tens of thousands of parameters. You pass a second image you have taken from your training sample, you pass forward pass, and it gives you another output, which again depends on these tens of thousands of parameters. Now, you sort of equate them to the true values that you actually desire. So you construct a sum of squares such that when the sum of squares is exactly 0, then your network has fully captured has solved the optimization problem perfectly. Although in a real world example like this, it never solves it perfectly. So because this is an optimization problem, you sort of you are after a global minima that also corresponds to something that that is generalizable or predictive on unseen data. Instead, it is most typical to get trapped in a local minima. But the advantage that neural networks bring here is that it sort of lifts the optimization problem to this very large number of dimensions. So it's a very high dimensional optimization problem where the your landscape of the loss that you have written down as sum of squares is sort of is quite different. So one can say that, okay, this is like curve fitting, and it is exactly that. So except that we have this neural architectures that are doing the job instead of, say, your favorite set of orthonormal polynomials. All right, so it seems to have trained this, and pursuant to the previous question, now these layers have been trained. So perhaps that is why it was colored in red before. So now this trained network has been, what it has achieved is it's now specified the parameters, right? So let me perhaps write down an equation to demonstrate what is the computational problem it has actually solved. So net was our LeNet was our architecture that was unspecified, and it depends on a large number of parameters. What are those parameters? Those parameters are the unspecified quantities in these weight and bias matrices. So what is the optimization problem it is solving? The optimization problem it is solving is a minimization problem for the loss. So in this case, I'm going to write a heuristic equation for this. So what I'm going to say is, if I take LeNet and act it on some input I, and subtract it from the true output, which are the labels that you already know from your training data. And I squared them and I sum over I to say length of sample, training data size. So this is the loss function here. Is basically the sum of squares, as we have seen in curve fitting when we are younger. So this is known as the loss function or the objective, and the loss function depends on a lot of parameters. So let's collectively denote them by theta, and the thetas are the parameters of your architecture. So I denote them by a subscript here.
And your question?
Yes.
So here in this loss function, you're summing over the entire sample space that you've taken. So let's say, for example, your neural network is really bad at recognizing only the letter or only the number 8 or only the number 7, for example.
Mm-hmm.
But the loss function takes it into account with all other things. How do you identify that, like the loss is maximized only at a particular type of input, basically? Right.
So that would be an outcome that you do not want. That would be a poor outcome.
Right.
So you can analyze this post facto. So you can say that, okay, let me find out what are the specific cases or inputs, or in our case, handwritten digits on which this architecture completely fails, and try and work your way backwards from there. This is, you're pointing at some very interesting issues here. So for example, in our class of handwritten digits, let's see how many different labels appear. So here it is. So, okay, let's also sort this. So 0 appears 91 times, 1 appears 113 times, 2 appears 102 times, and so on and so forth. 7 appears 107 times. Now imagine a situation where you sort of had only one example of a handwritten 7 in your data set that you were allowed to use for training. So that would lead to some difficulties. It sort of says that your data set is not balanced in that situation. Here there's some sort of a balance here. I mean, we can sort of plot this as well. It's sort of everything lies between around 90 to 110. So we were sort of good here. But then there will be situations where this is not the case. So for instance, when we were working with let's say predicting Hodge numbers of some Calabi-Yaus, and your training set consists of lots of geometries with small Hodge numbers, but a very small number of geometries with very large Hodge numbers, for argument's sake. And in that kind of a situation, your data set becomes biased or unbalanced. So what do you do with that? So there are a bunch of things you can do. So there's lots of techniques that help you upsample your minority cases. So here, if 7 only appeared, let's say, 1 time, how would you fix that situation? So one way to fix that situation is to say that, hey, I actually know that my architecture is translation invariant. So I'm gonna take that one example that I have of handwritten 7, and I am going to translate that picture, translate the 7 written in that picture to various parts. I might even rotate it if I have rotational symmetry built into our architecture, and that helps you generate more samples, and you can label those rotated or translated images with the same value of 7, right? So effectively, you can incorporate the symmetries of your physical problem to upsample your minority samples. And so in fact, this turned out to be quite useful in the case of complete intersection Calabi-Yaus, and finding out their predicting their Hodge numbers. And we sort of went about it in the following way. So I don't know if everyone is familiar with how a complete intersection Calabi-Yau is represented, but it's represented by a configuration matrix that collects degrees of polynomials, and that matrix has some permutation symmetries. So although there were examples of geometries which had small Hodge numbers, they were not large in number, but we could exploit that permutation symmetry to permute the configuration matrices to generate more data effectively, and that helps you. So in summary, well, I guess the takeaway message here is the more you know about your symmetries of your system, the more you can utilize it in your machine learning pipeline. And typically, as physicists or mathematicians, we might find ourselves in the opposite situation. We might find ourselves in a situation where we need to determine symmetries of a system, because as we spoke about last time, that's very useful information. And in fact, you can build entire theories out of just knowledge of symmetries of a physical system. So that's the harder problem. But there is a lot of increasing amount of work in that sector. So a couple of my MPhil students at the computer laboratory last year did their thesis on these equivariant architectures, or how to learn symmetries in a given system, as opposed to incorporating them in your machine learning architecture or pipeline. So now that we have discussed these two ways of incorporating symmetries, it's good to drive home the point by saying that, you see, in the architecture, we have introduced translation symmetry. Another way of incorporating symmetry is exactly what I was talking about just now, which is to upsample using the symmetries. And this is called data augmentation. So you can either build in your symmetry into your architecture so that no matter, so that it's sort of cognizant of the symmetries of your underlying system, or you can generate more data using the symmetries and use that in your training procedure. The outcomes are similar. All right. So coming back to the loss function, so effectively, this Lenet, when it was uninitialized, it had lots of parameters theta, and when you gave it a specific input I, it's called a forward pass. It generates some output, and you compare that output with the true output, which are the labels here, right? And you sort of take, you build this sum of squares, and you design, and you've written down your loss function. Now, there's various things to be said about this, and there's ton of literature, and ton of different approaches in this procedure. But the basic thing to be said here is, so although this is the full loss function, in a typical machine learning application, you do not try to minimize this directly. So you sort of, using gradient descent, you sort of take a stochastic approach to this, which is called, that approach is called stochastic gradient descent. So effectively, what that means is, so if this was your loss function, how would you go about it? So once you initialize it, your theta parameter, you think of theta as a very long vector. All right. So this is the basic step of gradient descent, right? We all know this, that we take a little step in the direction of the maximum gradient. And this is the setup of the optimization problem. But what you instead do in a standard or in a typical machine learning application is, you do not do gradient descent, you do stochastic gradient descent, which works beautifully for this kind of a setting. What that means is, you will take the same steps every time, but instead you'll tweak your loss, to make something called a some random part of the loss. So let's heuristically define this again. This is sort of defined in the same fashion, except now instead of the entire data set, I am going to have a random sample of some size, and that size is called batch size. So, in this case, we have 1,000 sample points. And the first loss function corresponds to the sum of 1,000 terms. However, in the second definition of the loss, which is a stochastic loss, we only assume that we know, let's say, 10 points. And we collect the sum of squares of those 10 points, randomly chosen, and we take a gradient descent step according to that. So originally we had this, and that sort of the full problem, but in reality, stochastic gradient descent, what it does is it keeps repeating this thing over and over again until, you know, some convergence criteria is met. Let's say you do this, I don't know, 20 times. This is called epochs, number of epochs. So number of epochs is the number of times your data will be seen by your training procedure. It can be 1 or 2 or 100. And batch size, batch size determines the number of data points you will consider before taking one gradient descent step. And again, there is no special choice for batch size and epochs. And there's a lot to be said about modeling experience in this kind of settings. But they have an immense effect on the outcome. So these are important parameters of the net pipeline. Any questions so far? All right. If
Very
not, yes, go on.
Oh, you're good. You're good.
All right. All right. Okay. So now let's return to, so now, you know, this step accomplished the task of training using stochastic gradient descent. Actually, you know, if you remembered how when it was running, it sort of was showing the optimizer it picked. There's various kinds of optimizers, you know, which are mostly gradient based. There's Adam optimizer, and you can have gradient descent with momentum. There's basically loads and loads of choices, and it's sort of difficult to know a priori what you know that might actually what an ideal one might actually be. So yeah, so nonetheless, let's continue with this example. All right, so now we have trained a network, and that network is denoted by this function net. Now it's no longer a function class. You have specified all the parameters, so it's a specific function. So let's apply that function to check what you know, how it works. So let's remind ourselves what sample the first data point was. It was this, right? So now if we inputted the first handwritten image, which is 4, and we pass it through the network, it should give something. Okay, it gives us 4, which is great, you know, because that's true. But that's sort of saying that, okay, you know, you have basically learned the training data for the first data point. So let's see how well it does. You know, when you compare it to the actual output. So here the actual output, you know, is of course the number 4. So let's count the number of times it's actually producing this, right? Producing a correct output on the training set. Sorry, I aborted this because this was going to give a very long output. Instead, let's tally. All right. So it seems like on the training set, it is 100% accurate. And this can, you know, make you feel very happy, or can cause alarms for the following reason. It can cause alarms because it might be indicative that there is overfitting going on here. Of course, which is a constant danger. So, but that can be mitigated. So if you have overfitting, then, a signature of that would be, how does the neural network perform on unseen data, right? So right now it has, amazing accuracy. So let's test it out on something that it hasn't seen. So let's create a new set. Now let's be careful here on what we test. So we do not want to test it on the sample. So we take the complement of the sample set in our full data set. So sample is of size 1000, data is of size 60,000. So let's test on some random selection of, I don't know, 10,000 points of this. This would be our validation set, right? So it should be of size 10,000. Yes, it checks out. Great. Now let's test this on the validation set. So all right, I'm going to put a monitor here so that we know how things are progressing. So while this is going ahead, maybe let me say a couple of other things. So there are various ways of mitigating overfitting. So typically, if you have a very small amount of you have some amount of data, but your architecture is very small, it means that there are very few parameters to optimize here, right? This theta set, are very few. And that will lead to overfitting. So having more parameters can help, but it might not be enough. So there are some advanced tactics that one can employ. One of them is called dropout. What dropout does is during the training process, it sort of switches off certain neurons in the network with a given probability. And that seems to have a measurable impact on how well your network generalizes or performs on the validation set. And there's sort of theoretical explanations of this as well. If you think about generalization in the context of the optimization problem you have solved, that's sort of very interesting territory, because there's literature from very recent times which are indicative of the fact that of the following fact, that typically if you're using stochastic gradient descent, you might be finding minima which are flatter, relatively speaking. And then there are claims that such flat minima correspond to more generalizable neural network models. But to my knowledge, there are some semi-theoretical explanations of this, but not a fully satisfactory one. So that there's sort of very many interesting problems or theoretical explanations that haven't been found for various aspects of this pipeline, especially generalizability of your neural architectures. Then another interesting thing to mention to this crowd of physicists and mathematicians is the phenomena that machine learners term mode connectivity. So imagine you are plotting this function loss, this full function, as a function of theta. Then a few years ago, it was reported that there are lines along this landscape in the theta space for which the loss value does not change very much. So they are kind of reminiscent of flat directions in physics. Then, of course, there are not only straight lines, but also curves. And presumably one can envision higher dimensional loci in the parameter space of theta, for which loss stays constant. So, there's various tools we can employ to understand that kind of phenomena. Algebraic geometry would provide a bunch of interesting tools to study the lost landscape. And there's loads and loads of interesting research happening in that space. So nonetheless, we sort of we have tested it, and now we have to see the outcome of what it has achieved. I did not end up accomplishing what all I wanted to go through, but I hope we were thorough enough for this example. So let's determine what the success rate is. Let's compute some accuracy. So, how to measure your outcome of a machine learning process is also something that is important to consider. So, in fact, here we can get away with a simple measure like accuracy. So here I'm sort of collecting the number of number of times it sort of managed to get the answer accurately, and compare it with how many times it hasn't. So, all right. Okay, so we have reached the end of this pipeline, and it seems like now we have built an architecture, which is this neural network we defined earlier, which when you throw a handwritten digit at it, it predicts with roughly 94% accuracy on a validation set of size 10,000. You're welcome to repeat this exercise over the whole data set, and presumably it will be quite similar. So effectively, what it has managed to do is learn from these samples, these 1,000 samples of handwritten digits, and we have built a predictive neural network model that's quite accurate, actually. So that's close to 94% accuracy. Yes. Any questions?
Question. So for this recognition of digits, also like the standard neural network with architecture with linear layers, it also works, no? And it also gives like similar accuracy. So
yes.
Why to use convolution layers here?
Because I wanted to talk about symmetries.
Okay. Okay. So then convolution, maybe if you have like more complicated problems, could be useful. So when you want to do this thing that you say, this translation, like.
Yes. So that's true. So in fact, as a physicist, it's surprising that the first of these equivariant architectures, architectures that incorporated symmetries, appeared in the 90s. But then nothing really happened. And just a few years ago, due to really nice work by Rishi Condor and Taco Cohen, now one can build equivariant architectures with respect to all sorts of symmetries. Think of gauge symmetries. You can also incorporate discrete symmetries. There's a very nice formalism to do that. You sort of the approach is that you can incorporate discrete symmetries by incorporating a relationship between the different weight parameters that appear in your architecture, such that that relationship gives you an architecture that is indeed symmetric. So symmetric architectures are quite useful, and typically I've seen these two approaches that in most real world problems, like predicting the next song in Spotify, you sort of don't care about precise knowledge of the symmetries, but if you have maybe this is a bad example, but imagine you had some knowledge of symmetries in this context, then a machine learner's approach would be to incorporate them in your pipeline, as we have here through translation symmetries. But in many physical situations, we might be trying to solve the opposite problem. So one problem that might exemplify this is the case of R symmetries in the context of string theory. So as we know that stability of a proton is contingent on it not decaying in the minimally supersymmetric standard model, because there are decay channels for that. So in MSSM, it's explicitly prohibited by the incorporation of some symmetries, which are these R symmetries. Now, in the context of superstring theory, these symmetries must be found as isometries in the internal space, say Calabi-Yaus. So if you're trying to build a phenomenologically interesting model of particle physics using, say, heterotic strings, you would want to work on a Calabi-Yau that admits these discrete symmetries, right? So, there's vast landscape of Calabi-Yau manifolds, and one might try to characterize all their symmetries. Now, prior to machine learning, I attempted a class of these problems for a class of Calabi-Yaus, and using classical invariant theory and some group theoretic insights, it was very hard to characterize all these symmetries. I mean, although we did find lots and lots of R symmetries, this problem of finding symmetries of a system is rather hard. And as such, it's sort of, it would be interesting to see how machine learning can find such symmetries, given a physical system. So there's this very interesting work that was done around 2009, if I remember correctly. It goes by the name Eureka. So there, the physical system in consideration was, if I'm remembering details correctly, was a pendulum, and by observing the position and momentum, and collecting that data, one was able to determine the symmetries and hence write down a Hamiltonian, and hence almost fully characterize the system. So this business of finding symmetries is quite hard, but there are increasing number of tools. So there are these equivariant architectures that I was referring to earlier that are quite interesting to deploy in this case, and there are many problems in physics or mathematics where application of machine learning to finding symmetries could be useful. Yeah, if you want to chat about it, we can.
Yeah, then the convolutional layers, okay. So you wanted to show it to us because you think they can help in this finding of symmetry. Nice. So
yes.
And you use them already? I mean, in this Calabi-Yau metrics things that you were using a lot?
So here I would think of convolutional layer as a proxy for symmetries of the system. Here, convolutional layer is actually useful because there is translation symmetry. As I was saying earlier, that it doesn't matter where you.
It's where the number, where the.
Yeah, but then equally you can have a rotational symmetry. You can have a rotational convolutional layer. That should also not matter. People try to classify pictures of cats and dogs and whatnot, and it shouldn't matter if your favorite dog breed is upside down or not.
Okay.
Yeah.
Thank you.
Right. I want to highlight one thing. Perhaps let me just show you one slide in the presentation. So one of my colleagues and I teach this course in the computer science department called Theory of Deep Learning. where we talk about a lot of phenomena surrounding neural networks, and effectively we try to understand what is the state of the art in terms of experiments and theoretical explanations of various phenomena in deep learning. And we have a constantly evolving set of papers that we read in this course, and if one is interested, I'd be happy to pass on some of the past papers that we have found interesting to read, or some of the papers we are considering reading in the coming session. And this course happens typically in Michaelmas, but this year we're going to have it in the Lent term, so in January. All right. So stop sharing.
Challenger, can you hear me?
Yes.
Yeah, so I just tried to look for that web page. It's currently offline, I think.
I think I must have jinxed it.
Okay. So it's
But you should look back.
okay. So, but yeah, yes, please do send the
All right.
yeah. Gabriel.
All right. So this was it for today, right?
Yes.
All right. Thanks very much. And let's clap a little bit.